And if Sheila, if you're ready, Dr. Sheila Thibeault of the Langley Research Center will talk about lunar environment and its effects on materials.
Can you hear me?
Yes.
Okay, well, thank you so much, Maria, and I do apologize for being late. When I went to switch sessions, I lost my internet. Anyway, I am back. Thank you for still including me. I'm going to talk about MISSY. MISSY is one of my most favorite subjects. MISSY stands for the Materials International Space Station Experiment. It began in 1999, and it was the very first science payload on the outside of the International Space Station structure. The purpose for MISSY is to provide a platform in the space environment for testing individual test specimens. Usually the specimens are materials, but they can be devices. And one notable thing about MISSY is that all specimens are returned to Earth after the space exposure so that we can analyze the post-flight specimens in our own laboratories and do an in-depth analysis. The purpose of this is obviously to determine the effects of the space environment on the specimens. Initially, the platform was two-sided, as shown in the photograph for MISSY 2. It is now a four-sided platform. Next slide, please. There are four orientations that we use for MISSY. Each orientation has a different environment, so it's important to pick the right orientation for the experiment that you're planning. The RAM direction is in the direction of travel of the ISS, and this direction has the highest atomic oxygen level. The hind RAM in the opposite direction is the wake direction. This is facing away from the direction of travel, and this essentially has no atomic oxygen. The zenith direction is facing away from Earth, and this provides the highest solar exposure. And then nadir is facing toward Earth, and that does have the lowest solar exposure. Okay, next slide, please. On this slide, I've tried to compare the LEO environment to the lunar surface environment. There is atomic oxygen in LEO, but none on the lunar surface. There is ultraviolet in both environments, micrometeoroids in both environments. There's orbital debris in LEO, but not so on the surface of the moon. There are charged particles, charged particle radiation, electrons, protons, light ions, heavy ions in both. There are extreme temperatures, thermal cycling, and vacuum in both. Now, the temperature extremes are more extreme on the lunar surface. There is microgravity in LEO, but then there's reduced gravity on the lunar surface, on Moon, about 1/6 that of Earth. In addition, on Moon, we do have secondary neutrons and dust. We've been hearing a lot about dust in this workshop. So in comparing these two lists, one can see that one can actually consider using the MISSY platform to simulate to a certain extent the lunar environment. One word of caution, though, I point out is if you're planning to do this, do not use the RAM direction, because that is the direction where there is the greatest amount of atomic oxygen. Next slide, please. On the MISSY platform, the platform itself, we now have some high-resolution cameras. In addition to getting our specimens back, there are some features on orbit that can help us see what is happening to our specimens as a function of time. And I am starting to find this useful myself. These high resolution cameras scan and take photographs about once a month. And here I have shown you the same material. It has been photographed 8 times from June 2019 to February 2020. And looking at the progression as a function of time, we can see that the material in this case is gradually darkening. So this is something we can see that's actually happening in space. Next slide, please. Here I have some data, again connected with these images. I have looked at the images for 70 different specimens from Missy 9 to Missy 13. These are images that I have. And in looking at these, I can see that 17% of them changed in color, and 6% of them changed in both color and texture. So again, this is helpful to me because we can see changes actually happening in space as they are occurring. Next slide, please. The duration of exposure, the space exposure durations do vary on Missy. It's kind of hard to predict what the length of your exposure is going to be when you launch. That is because the specimens are covered up from the space environment every time there is a contamination event, such as with the docking of a vehicle on the outside of ISS. But we can keep track of these periods when the specimens are covered and not being exposed, and then calculate the actual duration of exposure in days, hours, and minutes. So we do know what the exposure durations are. Next slide, please. In addition to the cameras, the platform now has temperature sensors, UV sensors, and QCMs. The QCMs are quartz crystal microbalances used for contamination measurement. Here we've plotted these data from May 2018 to December 2018 on the wake side of Missy 9, and you can see there are fluctuations in temperature and ultraviolet. The temperature extremes, the temperature does change, and there are extremes, but of course the extremes are not as great as the extremes on the lunar surface. Okay, next slide, please. With regard to some upcoming flights, the RAC payload I've listed here. Now, RAC is not a Missy payload. RAC stands for Regolith Adherence Characterization. This is a lunar payload, and the purpose of this is to try to understand more about how the lunar regolith interacts with materials. I mention this in a Missy talk because the same materials that are being flown on RAC are also going to be flown on Missy 16 in the zenith direction. And Miria, our session chair, happens to be the PI for this Missy 16 experiment. And with this experiment, we'll have a way to compare some of the results of the Missy exposure to a lunar exposure. So if anyone is interested in considering Missy for exposing materials for lunar applications, there are flights coming up, Missy 17 and Missy 18 and so forth, in
1 minute, Sheila.
In roughly 6 months intervals. Okay, next. Okay, that was my last.
That was good timing.
Yeah, my last technical slide. Thank you all, and I'll try to answer any questions.
Right.